Lesson 3, Logistic Growth. In this particular lesson, you should be able to see this differential equation here and recognize that it is logistic growth and be able to write the solution here. This is something you want to commit to memory. We will prove it in this lesson, but it behooves you to commit it to memory. Number 1, the question wants us to draw the slope field. Now, this is just to give you an idea of what logistic curves look like. So here's the x-axis, the y-axis, and there's going to be this horizontal band. It's not part of the slope field per se. I'll do the slope field in yellow. The slope field is going to go like this. I'm doing a real quick slope slashes, little lattice of points to give you a sense of what curves would look like. Now, that's what it looks like inside this horizontal band. Outside of the horizontal band, it looks a little bit different. They just come down like this. And then they would come up like that. So that's a very rough sketch of the slope field. For values up here, the logistic growth and simple bounded growth have the same graph, and that is also true down here. But inside this horizontal band, the curves will resemble an S shape. It's sometimes referred to as the S curve. Logistic curves often referred to as S curves. Again, a logistic curve though doesn't have to resemble an S. It could resemble an exponential decay or growth function. In number 2, it asks you to draw a curve such that the initial y value is between 0 and L. So I'll come over here, draw my axes again. This should really be the t-axis. I like that better as the t-axis, y-axis. Then here is our horizontal asymptote. This is our limit. Then our curve is going to go in this S shape. It goes up and then approaches the asymptote like that. Approaches y equals 0 to the left. And again, this is S shape. In part B of number 2, it asks for the limit as t goes to infinity of y, which is the limit as t goes to infinity of L over 1 plus c star e to the negative k L t. So if t is going to infinity, then this quantity here is going to 0, making our limit equal to L, which makes sense according to the diagram above. Now in part C, the limit as t goes to negative infinity of y would have the denominator getting large without bound, so the denominator would go to infinity, leading to a limit of 0. So both of those are consistent with the graph above. And again, that comes with the condition that y naught is between 0 and L. If y naught is bigger than L, then we have this graph over here, and y naught less than 0, we have the graph over here. In number 3, it wants to know what is the value of y when y is growing the fastest. So I want to optimize y. I want to find the local max for some y. So I'm going to take the derivative with respect to y of our dy dt. And that's going to be the derivative with respect to y of the derivative equation, ky times L minus y. Now I will distribute that to be kly minus ky squared. Then I'll take the derivative, and that derivative will come out to be kl minus 2ky. I'm trying to find the maximum y, so I'll take the derivative, set it equal to 0, and that will give me, after I simplify, y equals L over 2. I can verify that by taking the next derivative. So the derivative of the derivative again with respect to y, and that's always going to be negative 2k, which is less than 0, verifying that y is max at y equals L over 2. And this is always the case. Y will be growing fastest when we're at half the limit. If I come over here and look at half of L, here's L over 2, the graph is growing fastest at L over 2. Always. Now let's look at a couple examples of this logistic growth. Okay, so dp dt equals the equation as you see before you. Now this is written in a really nice form where I can see that this here is k, and I can see that this here is L. It fits the kp times quantity L minus p format. With that being said, let's write that down. K equals 0.0004 and L equals 250. Now we should have committed to memory that P equals L over 1 plus C star e to the negative big K L T. And I'm just going to plug these values in. So I have 250 over 1 plus C star e to the negative k times L, which gives us negative 0.1, and then we have T. Now we do have to solve for C star with our condition that P equals 50 when T equals 0, 250 over 1 plus C star times 1. That tells me that 1 plus C star equals 250 over 50, C star equals 4. So our final equation, P of T equals 250 over 1 plus 4 e to the negative 0.1 T. Example 2. Now even though this one is not written in the form Kp times quantity L minus P, we can manipulate it to be in the form. So I'll say that dp dt equals, I'm going to factor out a 5p, and that will leave me with 20 minus p. So as long as this p is alone, then we have the form. From this, I can determine that big K is equal to 5 and L is equal to 20. P equals L, 20, over 1 plus C star e to the negative K times L, 100 T. With our condition, 3 equals 20 over 1 plus C star. Therefore, C star equals, let's see, 20 thirds minus 1, 17 thirds. Final equation, P of T equals 20 over 1 plus 17 thirds e to the negative 100 T. And while we're here, it behooves us to ask, when will P be growing the fastest? P will be growing fastest when P is equal to, if you remember, half the limit, 20 over 2. So when P, the population, is 10, it will be growing the fastest. Example 3 certainly doesn't look like the form that we want. What I need to get is dp dt equal to kp times quantity L minus P. Let's work this out a little bit. Let's first get dp dt by itself, and that will be P over 50 times 2 minus P over 250. Now I have to factor out a 1 over 250 to get the P by itself. So dp dt equals P over, I'll just write it 50 times 250. Now when I factor out a 1 over 250 out of 2, it actually turns that into 500. See, if I would multiply it back in, it would give me 2 minus p. So there I have it. This tells me that big K is 1 over 50 times 250, and L is equal to 500. Gives me P equals 500, 1 plus C star, e to the negative k times L. Well, that's kind of nice. The 500 over this quantity here, so that's going to give me 1 over 25. 1 over 25 t. With the condition 25 equals 500, 1 plus C star, therefore C star is going to equal, now you'll want to do this arithmetic, 1 plus C star equals 20, so C star equals 19, and there we have it. 500 over 1 plus 19 e to the negative t over 25. That is our final equation, our final model for P, and P will be growing fastest when P is 250. Example number 4. Because of the limited food space, a squirrel population, P of t, cannot exceed 1,000. P of t grows at a rate, so here we go, we're talking about a rate, proportional to both the existing population and the attainable additional population. If there were 100 squirrels 2 years ago and 1 year ago the population was 400, about how many are there now? What is the squirrel population when it's growing the fastest? First thing, it's already defined that P of t is a squirrel population. Let's write our differential equation, dp dt, so the rate at which squirrels are growing with time is directly proportional, big K, to the existing, which is P, and the obtainable, which is going to be the 1,000 minus P. So this looks like the exponential growth and the simple bounded growth put together. The limit is 1,000, can't exceed 1,000. The initial population is, we're going to call that 100. So what I've decided to do is go back far in time, as far as I have data, 2 years ago, and I'm going to let 2 years ago be t equals 0, and the population at t equals 0 is 100. So that means 1 year ago we have t equals 1, and the population 1 year ago is 400. So now, that's what the question calls for. What is it now? T equals 2, and that's what we have to find. Okay, back to the differential equation, which has the solution P equals 1,000 over 1 plus C star e to the negative KL. Now we know L is 1,000, so 1,000 L K T, like that. We'll use the condition to solve for C star. So 100 equals 1,000 over 1 plus C star e to the 0. That's going to give us C star equals 9. I'll update our equation. P of t equals 1,000 over 1 plus 9 e to the negative 1,000 k t. So like the other word problems, we're going to have to use the condition to solve for k. I would press pause now, and then the solution will be revealed. And here we have the work for solving for k. K equals the natural log of 1/6 over negative 1,000. I've got to plug that back into the model, simplify my model like we've done before. The solution is revealed here in the blue box. See, this negative 1,000 in the denominator of k canceled out with the negative 1,000 here. Then we simplified our model to look like this. You should be able to do that with fluency now. Now let's answer the question, how many squirrels will there be now? Remember, t equals 2 for now. So if you plug that in, 2 into the formula, it's amazing. It comes out, no calculator needed for this, and it comes out to an integer. You do the math, but it comes out to be 800 squirrels. Isn't that awesome? I'm going to provide a quick sketch of this. Put it all together. This is the t-axis. This is the p-axis. We started 2 years ago. That's t equals 0, but 2 years ago we started with 100. So that was, let's say here, 100. And then it can't exceed 1,000. So that's here, 1,000. And then we have our S-curve. It goes like this, and then like this. And of course, the squirrel population is growing the fastest when P equals 400 squirrels. Now, let's lighten up the mood with talk of the Asian flu. Okay, a very contagious type of Asian flu is spreading through a city of 50,000 at a rate proportional to both proportional to both the existing already affected and the number not affected, the 50,000. If 100 people were affected today, blah, 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 blah. So first thing I notice is I have to write the differential equation. N is the number infected. The derivative of N with respect to T, our differential equation, is proportional to N and the difference between how many people can get it and how many people do have it. So in this case, our L is the 50,000. I'm going to index this to be yesterday, t equals 0, and yesterday there were 100 people infected. Today, t equals 1, and n at the 1 is 130. Okay, you should press pause and work this out. The fractions don't work as nice as the previous example, but you should be able to solve all of this. And here is our solution before finding k. Press pause, find your k, and then let's check up. And we have now the solution boxed in pink, which is just a nasty, cruel fraction as the base to t. But that's what it equals in the end. When we solve the answer to the question, they want to know how many people will be infected 7 days from now. We just have to be careful. 7 days from now is t equals 8 because now was 1. So n at 8 can be expressed like that. And just in case you're interested, that's approximately 808 people infected by this nasty Asian flu. And of course, we know that the flu is growing the fastest when n, the number of people with the flu, is half the limit, so half of the population. So when the flu is growing the fastest. All right, here we go. We're about to prove this, that when we have this differential equation, it leads to this solution. One last comment before I do the proof, though. Some textbooks, including yours, says dy dt is little k over L times y, L minus y. And that then leads to this, which is y equals L over 1 plus c star e to the negative little k t. I really do believe that my way is better, and I'm not just being pompous here. I like this because this can act as a constant of proportionality, proportional to y in the existing. This is a little bit finicky. When you do it this way, it still works out because what they're calling k, I'm calling big K times L. Or you might say that what I'm calling big K is what they're calling little k divided by L. See, their little k here is the same as my big K times L. At any rate, we're going to prove that the differential equation leads to this. Alright, let's begin. I'm going to start by separating the variables. So I have dy over y times L minus y equals big K times dt. Going to integrate both sides. And the integration of the left actually requires partial fractions. So for the purpose of the proof, I'm going to skip over that and wait to the end to do that integration. But it turns out that this is 1 over L over y dy plus 1 over L over L minus y dy equals big KT plus C. This integration is 1 over L, natural log absolute value of y, minus, see the negative here, minus 1 over L, natural log of L minus y equals big KT plus C. Going to use a property of logs, so 1 over L times the natural log of absolute value y over L minus y equals the big K T plus C. And then I'm going to multiply both sides by L. So natural log absolute value equals big K L T plus C. I'm going to exponentiate both sides and get rid of the absolute value in the same step. So we have y over L minus y equals C star e to the K L T. A step that should be familiar from lesson 1. Next, I'm going to say that reciprocal equals reciprocal. So this is going to be 1 over C star e to the K L T. Break up this fraction into 2 separate with the y the common denominator. So L over y minus y over y, which equals 1, equals, and then I'm also going to bring this quantity back up to the top, C star e to the negative KLT, so it's now in the numerator as a negative exponent. I'm going to add 1 to both sides, 1 plus C star e to the negative KLT, and then I'm going to cross multiply, and I have y equals L over, there it is, 1 plus C star e to the negative capital K L T. Excellent. We put a box around that and a smiley face. Now let's go back up and look at the partial fractions. I'll do that, let's say, in this pink color here. So I'm breaking this up into partial fractions, which is a over y plus b over L minus y. That gives me that a times L minus y plus b times y equals the value of 1. See, the coefficient here is 1. System of equations, well, let's see, b minus a is the coefficient to y plus the constant of AL has to equal 1. That tells me that b minus a equals 0 and tells me that AL has to equal 1. Therefore, a has to equal 1 over L, and also b has to equal 1 over L. That's why we got this and this. This is our A, this is our B. And that is the end of the lesson.